When we look at distributing an application over multiple cores, at a broad level, there are two ways we can do that. The first method is called as functional decomposition, where you take up an application, break it up into different functional modules, and spread each functional module doing different things on different cores, right? So this is called as functional decomposition. A very good example for functional decomposition is the TTI pipeline design pattern we spoke about in my last video, where each module we broke up the entire layer 2 into multiple components and distributed each of these components over different cores. The other way to do distribution of an application over multiple cores is called as data decomposition. The fundamental difference is, in data decomposition, we don't break up the task itself. Task remains as a whole, but we run multiple instances of the task as a whole on different cores. So we are not decomposing a task, but we are decomposing data. So a very simple toy example for this would be, you take, suppose you have you have to write a program which goes through a million element array and multiplies each element by 2, right? That is the simple toy application, and you want to run this over 2 cores. A simple way to do that would be to break the array itself into 2 parts. The first half of the array is processed by one program, second half of the array is processed by a second program, and you run both of these programs on 2 different cores. So this, in a sense, is data decomposition. Basically, the 2 instances which are distributed on 2 different cores, they are doing exactly the same thing but on different sets of data. That's called data decomposition. In 5GNR, there are many places where we can use data decomposition, where basically you take a task which does something and you run multiple instances of the task, each instance working on different sets of data. Now let us take one example and go into detail and explain this pattern in more detail, right? I will take the real-time critical data path of 5GNR as an example as to how we can use data decomposition to scale that over multiple cores. Let me write the block diagram of the real-time critical data path, what all entities are involved, and then we'll talk about how we can scale it using data decomposition. So there are 3 major functional blocks. The multiplexer, the RLC DL, which is real time critical, and then you have the MAC TB creator. So 3 different functional blocks, and we can even look at it like one whole as the real-time critical data path, right? So what happens here? So basically the multiplexer accumulates the resource allocations given to it by the resource allocation entity in every TTI. And suppose this particular user has got say 8 component carriers, then each component carrier would have done some allocation of resources. It could have done some allocation of resources for this user. A multiplexer accumulates all of these things. Then the overall total grant, it distributes this over multiple logical channels of the of RLC, right? So he gets resource allocations from scheduler and distributes this overall resource allocation as transmission opportunities or grant to every logical channel, which is every different RLC entity in that particular UV. And this RLC DL entity, which once it gets the transmission opportunity in the TTI, he will pull out RLC SDUQ, SDUs from the queue, and basically formulate RLC PDUs for each of these things and pack them in the TB structure that has been allocated to him, and then pass the RLC PDUs to the MAC-TB creator, and this MAC-TB creator in turn could have got some MAC-CEs to be transmitted out for that particular UE in that TTI. He will create the entire TBs and then he will send it out to phi. Right? So this is the entire real-time sensitive data path portion in 5GNR, right? So now you want to scale this. Now, as you can see, the scaling dimension of this entire module is scheduled users per TTI. And of course, throughput and packet rate. So these things matter, of course, but it scales majorly on scheduled UEs per TTI. So if, say, for example, you're supporting 20 UEs per TTI in your system, then all the 20 UEs will have to be processed by each of these modules in the TTI, and for each of the 20 UEs, whatever data is there, that whatever resource allocation is being granted, they all have to be processed, and the RLC PDUs have to be created, the MAC PDUs have to be created, TBs have to be created and shipped out to phi. So this is the job of this entire module here, right? Now, a simple way to apply data decomposition in this place is keep this entire entity as is, do not break it into different cores, right? But have multiple instances. So RT critical data path 2. And so on, right? Multiple instances, and in every TTI, if you got 20 UEs, you give 10 UEs to this instance and the other 10 UEs to this instance to be processed. And if you want more instances, suppose you have 4 instances, you could give 5 UEs per TTI each to each of these instances. That way you scale up, right? You can scale to any number of UEs per TTI that way. And overall, say for example, so basically if you have 1 core capacity for running this, by running 4 instances of this, you run it on 4 cores, you scale to 4 cores capacity without splitting the application itself. The entire application as is sits on the same core, but you have multiple instances of that running on different cores and hence achieving scale. So suppose you had 20 UEs per TTI to be supported, you run 4 instances and you get 5 UEs per TTI in each of these instances. Suppose it cannot, it all depends on profiling again. If your single instance can support 20 UEs per TTI and the throughputs that you are desiring in your system, then it's fine, you don't have to split. But if you say figure out that based on profiling that, with the kind of throughputs that I want to support, 1 instance of this RT critical data path can support only 5 UEs per TTI, then we run 4 instances of this entire module on 4 different cores, each of them supporting 5 UEs per TTI, and overall as a system, we can support 20 UEs per TTI. That in essence is your data decomposition as applied to 5G NR RAM. So that's about data decomposition. Now, while this is very, very helpful in scaling the overall system capacity and the system throughputs and system scale, right? But there is still one problem that we have to solve. Here we have scaled by distributing UEs to different instances of the RT critical data path. How about single UE throughput itself? Single UE throughput is very, very important in many use cases, like say fixed wireless access, or there are some trunking solutions, all of these places. Single UE throughput also becomes very, very critical. So that is where it becomes tricky, because data decomposition cannot be used for scaling single UE throughput unless you go to the extent of I will support single UE throughput only if it has got multiple bearers, right? If it has multiple bearers, then even if you look at it, this entire entity can be split to be data decomposed at the granularity of bearers, not UEs, right? So we could even do that, but that has dependencies, like you should tell the operator that you can support it only if you have multiple bearers in a UE and all those things. But that is some restriction. We don't want to go there. Another way to scale single UE throughput in this case is, if you look at it, this multiplexer entity and the Mac TB creator entity, these are per cell entities as well. So you could even go to the extent of making these instances on a per cell basis, per UE and per cell basis, and distribute UEs to these instances which are also per cell, because these two belong to Mac actually, the multiplexer and Mac TB creator. They are Mac entities, and Mac is aware of cells. So you could, like, suppose you have 8 component carriers in CA, you could distribute these entities on a per cell basis and get more cores to run on and more threads to run on and scale further for single UE throughput. But then this RLC DL entity, right, which is pure RLC entity, which is not aware of cells, you cannot scale this on a per cell basis. So this is where it becomes tricky for scaling single UE throughput. And RLC DL, this entity, which is basically processing your TX opportunity, can become a bottleneck. So how do we solve this issue? Fortunately, 5G NR protocol updates have help us in this area. In in LTE, there was this concept of RLC concatenation, where you have any number of RLC STUs coming, and only when the grant comes, a single RLC PDU could be created by an RLC entity by concatenating all the RLC STUs. So RLC PDUs could not be formed in advance, right? So that is one issue in LTE. And further, even the MAC protocol header, right? It used to be a common MAC protocol header for all MAC SDUs. For all MAC CEs and MAC SDUs, there was one common MAC header. So MAC header could also be composed at the fag end when you had all the MAC SDUs lined up. So basically what that forced us to do in LTE is, you had to do RLC PDU formation and MAC PDU formation, both of these in the RT critical data path itself. We did not have a choice. However, in 5G NR, the protocol updates are there, where what we are doing here in 5G NR is RLC PDUs. There is one RLC PDU for every RLC SDU. So basically the RLC header comes for every RLC SDU. So basically RLC PDUs can be prepared in advance as soon as you have an RLC SDU. So what you can do is, you can delegate move RLC PDU creation to non-real-time RLC or RLC upper. This is one thing. Second thing is, since even in Mac, every Mac SDU has got a Mac subheader. Together they called as Mac sub PDU. So these things also, you can create Mac sub PDUs also in advance without waiting for a grant. So there's no common Mac header that you have to create, which can be created only when you have all the Mac SDUs ready, lined up, right? So move Mac sub PDU creation to non-real-time RLC. So this, which is the bottleneck, right? This bottleneck, by moving away two major work parts that this entity had to do, to RLC upper, which is non-real-time critical, which is not TTI bound, we are freeing up this module by moving two major activities that it had to do in 5G NR. We could not do this in LTE. So now the RLC DL entity has very little work to do. All it has to do is, basically it has got Mac sub PDUs, including the RLC PDUs, everything created in the queue, which is coming in for RLCDL. It has to pick these, pack them into the TB structures allocated by the multiplexer. And only thing it has to do is, if for example the grant is not sufficient to take a complete max sub PDU, it will have to segment the last RLC SDU, and at that point of time it has to apply corrections to that particular max sub PDU and RLC PDU created, because you ended up splitting that particular RLC SDU. So that correction has to be applied by the RLC DL entity. Otherwise, it has got a lot of work, already done by RLC upper, so it has got the PDUs ready for it. So this is a very important optimization we can do in 5GNR. So with that, we can scale this entire module, the RT sensitive data path, by using data decomposition, by distributing them over this entity over multiple cores, by using data decomposition technique. So this in a sense is, this is a good example for data decomposition in 5GNR. There are other ways, like say even PDCP can be scaled, PDCP entity also can be scaled using the same technique. Different users could be given, different users could be mapped to different PDCP entities, and each PDCP entity working on different cores. So that is an example. Then there are many instances where, when you have a lot of carrier aggregation, then some of the scheduler entities could be running on a per cell basis, exactly the same work it does as scheduler, but they could be a different resource allocation entity. For example, there could be different resource allocation entities working on different cells. So that is also an example of data decomposition. So if you look at it overall, 5GNR scaling, right, you employ functional decomposition to basically make the code more modular, and also use data decomposition where necessary to scale where it makes more sense to apply data decomposition, like for example in this case. And one of the biggest advantages of data decomposition is it's easy to scale up and scale down. Like say example, this entity, suppose we want to scale up, we run more instances, that's all. There's no code change, only the load balancing logic, the distribution logic of the work into different threads, the mapping of UEs to each of these threads, they have to change, but the code itself doesn't have to be changed. However, you take the TTI pipeline, which is an example of functional decomposition, to scale up or scale down. Like suppose I defined a 3 TTI pipeline, I want to make it a 6 TTI pipeline. I have to further break up the modules itself into submodules and define interfaces between them. There's a lot of code change, a lot of design change involved, and it can become very complicated to scale up or scale down a functional decomposition based scaling. Whereas any data decomposition based scaling you have, it's very easy to scale up, scale down elastically based on demand. So that's all I had in today's session, friends.